Tension. What is it? It's difficult to understand, so let's take a look at an example. We have some object with mass m attached to a string. Let's draw a free body diagram, downward force of mg, and an upward force of tension. We say the object is acted upon by an upward force of tension. This phrasing can create some misconceptions about tension and what it is. Tension is the resistance to being stretched by an applied force on either end of the string. Let's draw a free body diagram on the string. The string is not increasing in length, and therefore, well, let's look at it on an atomic scale. The tension is essentially the force by which the atoms of the string hold together as opposed to being broken apart. But how do we quantify tension? Draw the string again with the same applied forces. Now, let's cut the rope with our trusty pair of scissors and attach our new ends by a spring scale. The spring scale will actually tell us what the force of tension is, the force necessary to resist being stretched by the applied forces. Again, if the string is not increasing in length, then it's going to be resisting the two applied forces, and therefore must have a force going back into itself. Kind of. It's that resistance. So that kind of corresponds with Newton's third law. Newton's third law says that for every interaction there is a pair of actions or forces, impulses, etc. that act on the two interacting objects that are equal and opposite. Tension can very easily be explained using this law. Imagine a string attached to a wall on one end, and on the other end there's me pulling on the string with 50 newtons. The string is not accelerating, so the wall must be applying a force of 50 newtons in the opposite direction of my pull. The common mistake is to add the forces and say the tension force is 100 newtons. In reality, the tension force is actually only 50 newtons. Let's focus on the segment where I'm pulling. It is keeping me from accelerating with my force of 50 newtons, and therefore resisting me trying to stretch the string with its tension force. Since I am not accelerating, this tension force must be equal and opposite, 50 newtons. This free body diagram looks like there are 50 newtons acting on me, keeping me in place. But again, don't be confused by the tricky wording. Okay, let's look at a classic tension problem. Classic tension would involve an Atwood machine with an ideal pulley, no friction, and between the string and the pulley, and a massless string. A massless string with tension has equal tension throughout each point of the string. I'll explain further shortly, but for now let's draw two free body diagrams of each object. The 2 kilogram object with a downward force of 20 newtons and an upward force of tension. The 5 kilogram object with a downward force of 50 newtons and an upward force of tension. Sorry about my sneeze. Now, let's use Newton's second law to help set up our equations. But we must figure out in which direction the system will be accelerating. Any ideas? The 2 kilogram object will be accelerating up towards the pulley, while the 5 kilogram object will be accelerating away from the pulley. So, our first equation, we get T minus 20 newtons equals 2 kilograms times acceleration. And our second equation will be 50 newtons minus T equals 5 kilograms times acceleration. And you just have to make sure you know in which way the system is accelerating to get those equations. Since their acceleration will be the same and the tension forces are the same, the string is because the string is massless and the tension force is the same, we may treat this as a system of equations to solve for tension. Now, as I slowly figure this out, let's talk about why a massless string must have equal tension throughout. It satisfies Newton's second law. If the string had equal tension throughout, the sum of the forces would be zero in a static case, which must be true because the other side of the equation, mass times acceleration, would be zero since the string has no mass. However, even on a string with mass, what I said at the beginning holds true. If two adjacent points or atoms on a string with tension were looked at, they would have an equal force of tension at those string ends. But a different force of tension if another set of points were chosen to be looked at. In other words, move the string scale to a different snip in a massive string with tension, and the shown force of tension will be different. I hope this helped explain tension. Good luck, y'all.